Hello everyone. In the series of lecture on solid-state chemistry, today is the fourth lecture and today's subtopic is lattice planes. So let's start with the definition of lattice planes. This is the definition of lattice planes. It is defined as the points in a space lattice may be arranged in a large number of ways in a series of parallel and equidistant planes covering all the lattice points, which are known as the lattice planes. So this is the definition of lattice planes. That means the space lattice. Space lattice means the spatial arrangement of the lattice points. Okay, so the lattice points here these points are actually the lattice points in a space lattice may be arranged. So they can be arranged. Now in several ways they can be arranged. Okay, now in such a manner they have to be arranged in such a manner that they should be parallel and equidistant. Okay, so and not only that, they have to cover all the lattice points. That means no lattice plane should be left uncovered in order to make a lattice plane. So these planes, these imaginary planes actually are known as the lattice planes. So what are the main characteristics of lattice planes? The main characteristics of lattice planes is that they must have to cover all the lattice points. That means no lattice point should be left uncovered. Number 2, they should be parallel to each other, and finally number 3, they should be equidistant. That means the distance, the perpendicular distance between them should be same for all the lattice planes. That means they are all equidistant. Now the indexing system of the lattice planes. There are two types of indexing system. One is the Weiss indices and another is the Miller indices. Let's begin with let's discuss here first the Weiss indices. Okay, so this is an old convention, and by the Weiss indexing system we have to do this. We have to do this like this picture. In the terminology of crystallography, x-axis is actually described as a-axis, y-axis as the b-axis, and z-axis as the c-axis. Now suppose this is some lattice plane and this is cutting the three axes at different distances, such as it is cutting the intersecting the x-axis or a-axis at h prime distance, it is intersecting the b-axis at k prime distance, and for c-axis the intersection takes place at L prime distance. Okay, so how would you describe this lattice plane? By means of Weiss indices. Suppose A, B, C are the h lengths. Okay, A means here this point to this point, this distance is definitely A. Here to here is also A. Here to here A. Here to here A. You all know that this is the cell parameter. So what is the B distance? This to this distance, or this to this distance is B. And the distance from this point to this point is C. This point to this point also C. Now these are the edge lengths. Now at what distance they are intersecting? The corresponding axis is H prime, K prime and L prime. So H prime is the intercept of the planes along x-axis, K prime the intercept of the plane along b-axis or y-axis, and L prime is the intercept of the plane along c-axis or z-axis. Okay, now then their Weiss indices should be like this: H prime by A, K prime by B and L prime by C. That means the fraction or the ratio of the intersection, distance of intersection from the origin and the edge length. That means suppose this is intersecting a half distance. Okay, then half by 1, that is half is the Weiss index of 1 point. For the second axis, suppose this is cutting at 1/3 point. Okay, so at 1/3 point it is 1/3 by 1. That means 1/3 A by A, or 1/3 B by B. So this A, B, B, C, C are cancelled by each other, then 1/3 only remains the same. Or for example, suppose this point from on the A axis, the plane instead of intersecting at this point, it is intersecting at this point. Suppose at 1.5 into A distance. Okay, then what should be the Weiss index? Weiss indices? The Weiss indices should be 1.5a divided by a. So the H prime value is 1.5a. So the Weiss indices should be along the x-axis 1.5a by a, that is 1.5. Okay. So this is about the Weiss indices. But okay, we have to elaborate with some examples before going to the next one. Okay. This is, suppose take the plane which is parallel to the BC plane. BC plane means YZ plane, that is, it is actually perpendicular to the A axis. Okay. So what should be the Weiss indices of this plane? Actually this plane intersects the A axis at a distance, and they are parallel to the B axis and parallel to the C axis. That means they are intersecting at infinite distance. So their Weiss indices are 1, infinity, infinity. Similarly, the plane which is actually perpendicular to the B axis, that is the XZ plane or the AC plane, it should intersect the B axis at B distance, but it is parallel to the A axis and parallel to the C axis. So it should have the Weiss index infinity, 1, infinity. Similarly, the AB plane which is actually perpendicular to the C axis has the Weiss indices infinity, infinity, 1. But this Weiss index is an obsolete process. This is an old convention. Okay. The new convention of indexing the lattice planes is Miller indices. Miller indices of a plane can be expressed as HKL. Okay, the intersection H prime, K prime, L prime, but the expression of Miller indices are HKL. So what about HKL? HKL is actually the reciprocal of the Weiss indices. Okay, if that one is H in the Weiss index is H prime by A, then in the Miller indices it is A by H prime. Okay, so this distance, suppose half distance. Okay, half distance now becoming A by half into A, that means 2. Suppose this is 1/3 distance, that means B divided by 1/3 into B, that means 3. Suppose this is also half distance, so it should be C by half into C, that means 2. That means the overall Miller indices of this plane should be 2, 3, 2. Okay. And here the same thing, H prime, K prime and L prime, they are the intercepts along the x-axis, A axis, B axis and C axis. Now let's move on to the next topic, which is interplanet distance. That means the perpendicular distance between the two planes. Okay. Now we have some unit cell, and that unit cell has the cell parameters A, B, C, and it has some lattice plane which intersects the A axis at P, the Y axis at Q, and the C axis, Y or B axis at Q, and the C axis at R point. Okay, and the perpendicular from O on the plane, from the origin on the plane, touches the point M. Okay, that means OM is perpendicular to the PQR plane, and along O point there is another lattice plane. Okay, so this distance from O to M is actually the interplanet distance. So we have to find the value of OM here. Now on the A axis it is making a triangle. Actually it is making 3 triangles. Along A axis one triangle, along B axis another triangle, and along C axis the third triangle. So along A axis it is forming a triangle OMP. Along B axis it is forming a triangle OMQ, and along C axis it is forming a triangle OMR. So these are the 3 triangles, and this line OM is actually making the angles P, Q and R with the A axis, B axis and C axis respectively. This is OM. OM means this OM is this OM. Okay, and this RM is actually this RM. So this RM is actually the perpendicular, and OM is the base, OR is the MO is the height or perpendicular, MP is the base, and OP is the hypotenuse. What about this triangle which is being formed along the B axis? Here OM is the base, okay, MQ is the perpendicular, and OQ is the hypotenuse. Now about this triangle, you can take OM as the base also, then MP as the perpendicular. In that case it would be similar like this and this triangle, okay. Now let's see the coordinates of the point P, Q and R. The lattice plane which is intersecting the A axis is the point P, and it is actually at a distance A by H along the A axis, okay. So the coordinate of this point should be A by H 0 0, because it has no movement along the B axis or C axis. Similarly, the coordinate of the Q point should be 0 B by K 0, and the same for R should be 0 0 C by L. This point, this line OM is the interplanet distance, which is also written as DHKL, okay. Here OM perpendicular to MP, OM perpendicular to MQ, OM perpendicular to MR. For triangle PMO, this PMO triangle which is actually formed along the A axis, for this triangle OP is the hypotenuse, PMO is angle P, and therefore cos P equals to OM by OP. That means OM is D and OP is A by K, so this is actually KD by A, okay. Now for our convenience, DHKL is simply written as D. Here an L should be added. DHKL should be simply written as D. That means next time we shall write just D, or here also we have written D, but this D is actually this HKL. Thus we have got equation number 1. So what is equation number 1? Equation number 1 is cos P equals to KD by A. Similarly, for the triangle QMO and for the triangle RMO, we have got equation 2 and 3 respectively. What about equation 2? Equation 2 is cos Q equal to HD by B, and equation 3 is cos R equals to LD by C. Now we have to apply the cosine rule. What is the cosine rule? The cosine rule is cos square P plus cos square Q plus cos square R equals to 1. So this cosine rule is applied. So we have got the values, corresponding values, okay. So cos P is HD by A, okay. Similarly cos Q is KD by B, and cos C is LD by C. So taking whole square, so this is H square D square by A square, this is K square D square by B square, and this is L square D square by C square. Now this D is taken as common and taken to the left hand side, then it goes to the denominator. Here we have written instead of D, DHKL, okay. So this is actually DHKL's whole square. So 1 by DHKL's whole square is equals to A square by A square plus K square by B square plus L square by C square. So this is the interplanet distance, a relationship for interplanet distance with HKL with A, B and C. Therefore DHKL should be the inverse, that means should minus half power of this overall parameter, okay. So for a cubic system, A equals to B equals to C, in that case it reduces to A by root over H square plus K square plus L square. So this is interplanet distance for a 3D plane. If the plane is two-dimensional, okay, that means only two axes are mentioned, then in that case it is applied by simply by using the cosine rule again, but this is more simple. This is one plane, this is another plane, okay, and it is intersecting the A axis at P, the Y axis at Q. The coordinate of P is A by H comma 0, and the coordinate of Q is 0 comma B by K. and OM is the DHK. Here L is omitting now. Okay, here L is omitting. And for our simplicity, this DHK is simply written as D, small letter d. So let's start. PQ, P prime, Q prime are the 2D planes. Okay, P prime, D prime is one 2D plane and PQ is another 2D plane. OM is perpendicular to PQ. Definitely OM is perpendicular to PQ. And the angle, corresponding angles, POM is this angle and QOM is this angle. These two angles are P and Q respectively. For OMP, for the triangle OM and P. Okay, what is the hypotenuse? Hypotenuse is nothing but OP. This is the hypotenuse. Okay, then this is the base and this is the perpendicular. Then cos P must be base by hypotenuse. Base is OM, hypotenuse is OP. So cos P is OM by OP. The value of OM is D and OP is A by H. So it is HD by A. Simply the value of cos Q is KD by B, and when they are combined with the means of cosine rule, cos square alpha cos square beta equals to 1 or cos square P plus cos square Q equals to 1, then it gives the result 1 by D square equals to H square by A square plus K square by B square, or D equals to H square by A square plus K square by B square whole to the power minus half. Okay, and for a cube, A equals to B, in that case D equals to A by root over H square plus K square. Now 110 plane, 100 plane and 111 planes for 4 space lattices. You have to draw these pictures. You have to draw all the 4 into 3, 12 pictures. Okay, this is primitive 100 plane. So this is intersecting at just unit distance along the A axis. This is 110 plane. 110 plane means it is intersecting the A axis and B axis, not the C axis. It is parallel to the C axis. Whereas 111 plane means it is intersecting all the 3 planes, all the 3 axes at unit distances. So the interplanet distance from the formula of DHK, we can find out that D100 is A, D110 is A by root 2, while D111 is A by root 3. But the twist is here. The twist of the story is here. Here, all the conditions of making lattice planes are not fulfilled when you will try to make 100 plane for a face-centered space lattice. Why? Because if you draw this plane and this plane, then in between these face-centered atoms or the lattice points are remaining uncovered. But what were the 3 conditions? The condition number 1 was the lattice point, all the lattice points should be covered. No lattice point should be left uncovered. Okay, in order to do that, we have to input one more plane in between 2 planes. So this 100 plane no more remains 100 plane, it becomes a 200 plane. Similarly, the 110 planes also become 220 plane, while in case of drawing the 111 planes, all the lattice points are covered, so no need to input or insert any more lattice plane in between these 2. So the 111 plane for a face-centered space lattice still remains a 111 plane. Now let us find out the value of their DHKL, that means interplanar distance. The DHKL value should be here, not A, it should be A by 2. Okay, just put 1 by root over 2 square plus 0 square plus 0 square. So root over 2 square means 2, so it should be A by 2. Similarly, this should be 1A by root over 2 square plus 2 square plus 0 square, that means 2 root 2. But this one is A by root over 1 square plus 1 square plus 1 square, that means A by root 3. Similarly, for body centered space lattice, the 100 plane is actually the 200 plane and 111 plane is actually 222 plane, while the 110 plane can cover all the lattice points, so 110 plane remains unchanged. And similarly, the distance between the lattice planes should be D100 is actually D200, has the interplanar distance A by 2 for D110. It is remaining unchanged, so look here, A by root 2, here also A by root 2. but the D111 plane becomes D222 planes. So the interplanet distance should be a by root over 2 square plus 2 square plus 2 square. That means root over 12. That means 2 root 3. Okay, so that is why it is a by 2 root 3. For a base-centered space lattice or a C-face-centered space lattice, we have 100 plane, actually 200 plane, while 110 plane remains unchanged. On the other hand, 111 plane also remaining unchanged. So these two values should have the same value with the primitive space lattice, while this value should have the same value with the face-centered space lattice or the body-centered space lattice. So look, this is a by 2, similar with these two, while this is a by root 2, similar to this one, and this one also similar to this one, which is actually a by root 3. So that's all about the lattice planes of a unit cell or a crystal, which is very important in order to find out the entire crystal structure with the help of X-ray crystallography. Okay, next, our next topic is X-ray crystallography. So that is for that the lattice planes, the topic on lattice plane was very important. Okay, so that's all for today. Thank you. Have a nice day.